stressful school day. This is what happens when you do well at math. Today, wait, crap, I gotta do like a good little intro. Hey, what's up? Today, we're gonna be learning about a brand new section. Oh, you know what section it is. Section 5.3. The title is, that was probably sick. Inverse functions. The simple definition of an inverse function is a function that reverses another function. Like this. Am I upside down? Dope, okay. This is how you're gonna call it an inverse function. You're gonna put a little negative one. Honestly, this should all be review for you guys. You should know what an inverse function is. But just in case you forgot, this is what it's gonna look like on your paper. Get this down, obviously. I'm gonna paint a pretty picture with circles to try to represent what an inverse function is. Here, we can see the basics of an inverse function. So the domain of f is gonna equal the range of the inverse function, and vice versa. So the range of the function is going to equal the domain of the inverse function. So x is going to equal y, and y is going to equal x, and blah, blah, blah. Here's another fun way to define a inverse function. An inverse function. The f of g of x is going to equal x for each x in the domain of g of x. And g of f of x is going to equal x for each x in the domain of f of x. Kind of complicated definition, but this is just if you want to triple check that your inverse is correct. This only applies if g of x is the inverse. Let me write that down. It's time to talk about what we've all been thinking about, and that is the horizontal line test. Probably already know this again, but this is a way to verify that a function has an inverse function, because that's a big thing. You can't just go around throwing on an inverse function on any function. No, it must pass the horizontal line test, and there are two conditions to that horizontal line test. The function must be one-to-one, and in order for it to be one-to-one, it must be monotonic. You don't really need to know that word, but basically it just means, I don't know what that means. Basically means that it has to be strictly increasing or strictly decreasing in whatever its domain is. But I'm going to paint a pretty little picture, and it's going to make a lot more sense with the graph. So graph time. Let's look at this graph. It's a beautiful one, but is whatever function this graph is representing going to have an inverse function? I don't know either. We should probably do a horizontal line test. That's literally all it is. Okay, riddle me this. Does this horizontal line pass through more than one point on said graph?
Yes!
It does! You know what this means? This means it does not have an inverse function. It doesn't. It failed the horizontal line test. I'm going to show you a function that passes the horizontal line test, so we can take the inverse of that function, because that's why we're all here. Let's take a little look-see at this function. And what do you think we should do? I think we should apply the horizontal line test to it, because I don't know about you guys, but I want to take the inverse of this function. Let's make sure we can do that. That is so exciting. You know what that means? That means we can take the inverse of this function. And lucky for you guys, I know this function. So let's take the inverse of it. Let me teach you how to take the inverse of a function. Here is our function, square root of 2x minus 3. Now, we already concluded that it is monotonic, or that word. It passes the horizontal line test. It's one-to-one, so we're all good. Let's take the inverse of this function. Basically, all you're going to want to do is get the x alone. So All right, we need to get the x by itself. So first thing to do is you're going to square both sides. Get rid of that pesky square root symbol. It's not that hard. Now we have y squared equals 2x minus 3. I wonder what we do next. Come on, guys. Add 3 to both sides. Y squared plus 3 equals 2x. So now we're here, divide everything by 2. And we're going to be left with this equation right here. Oh, wait, no. And it looks a little funky to us, right? Because we're not used to seeing the x by itself. We're used to seeing a y by itself, right? Well, that's great, because we're about to switch the x and the y. I know, seems kind of crazy, right? But that is how we get the inverse function. There you go. You've done it. You just found your inverse function. You can switch the y to our correct notation. Boom, there's your inverse function of that original one. Thanks, hopefully. We found the inverse function, but we gotta connect this back to the original definition, which is domain equals range and range equals domain, or the inverse function versus the original function. This is the inverse function we found, and this was our original function. This was the original function, and this is a graph of the inverse function. Let me color coordinate really quick. There we go. Connection. You can see here that the coordinates have basically just flipped. X has become y and y has become x. I'm all happy. You should be all happy too. Here I have also drawn a dotted line. This is the axis of reflection for the functions. That gives you a better picture of what this inverse function is supposed to do. Ugh. I am craving some calculus here. So far, it's just been blah, blah, blah algebra, right? It's time for some calculus. Let's see how derivatives of inverse functions can be useful and how to take them. Spoiler alert, taking the actual derivative of the inverse function is basically the same thing as taking a regular derivative, but we can use them in a super fun way to find the derivatives of normal functions. This is the problem. Find the derivative at the given point. This is what you're given. X equals y cubed minus 7y squared plus 2 at the point -4, 1. This is a very simple inverse equation, but I feel like it gives a good example of how they can be useful. First step, we need to recognize that this is already in the form that we like. We love this form when we're dealing with inverse functions because the x is already by itself. Remember? We can just skip a bunch of steps and immediately switch x to y and y to x. But don't forget your notation or else you'll get confused. Okay, we did that. Y equals x cubed minus 7x squared plus 2 at, wait a second, can't we just use the original points given? No! Let's not forget what we learned in the beginning, x equals y and y equals x with inverse functions. So what are our coordinates going to be? 1, -4. This is our inverse, right here. Inverse of the function equals this. Now we simply take the derivative. I think we all know how to take a basic derivative. This is a pretty easy one. There's your derivative. You gotta put parentheses around that because the dashes can get kind of confusing. It's calculus. Now we have our derivative and we have our point. So what do? We plug in our x. So when you plug in your x, which is 1, you are going to get, it's going to equal -11 because 3 times 1 equals 3 minus 14 is going to equal -11. But wait 1 second. Didn't the original problem ask us for dy over dx? The derivative of the normal function, not the inverse function? Good thing we have this amazing theorem. Amazing. This is a theorem that's pretty important right now, and it states that g prime of x equals 1 over f prime of g of x equals 1 over f prime of y, which equals 1 over dx over dy. This can be heavily simplified down. I like this one a lot better. Look how simple this looks. This says that dy over dx equals 1 over dx over dy. So in our problem, that's going to look like this. There we go, right there. This was our original answer, and we can state from that theorem that f prime of x equals 1 over negative 11 calculus words at the given point negative 4, comma 1. There's your answer. We used inverse functions to find the derivative of an annoying problem that was in an annoying form. I'm happy. All right, so what did we cover in 5.3, inverse functions? We covered what it takes to be an inverse function, how to get an inverse function, and how to use inverse functions in derivative situations. Wait, how do I wrap this up? God, okay. Good job. Just make sure passes those tests. Don't miss a step. Steps are important in this section, and you're gonna rock it. Thank you for watching.